So I already graded the exams, but there's a couple of students that are I'm still waiting for them to take the exam. There are queues, so I have to wait for them to be available. So as soon as those students are able to complete the exam, then I'll bring the exams back. Promise was good. So we'll discuss the exam in class once we complete the process. I have no control over when they're coming back. Is what we're living right now. So, but I promise, as soon as we get those students through the process, then we go through the exam, and you have an opportunity to ask questions and to talk to me and so on. So it's working. Okay. Okay, so on Wednesday last week, we continue our discussion on the Simplex Method. And we discussed some examples in class, actually one example. So I want to go through that one more time. This second part of the semester will depend highly on this algorithm. So I want to make sure that you understand what we are doing, because we're going to go back to this and we're going to do more things using the algorithm. So today I'm going to focus on going back to talk about the steps, how to solve these problems. We're going to also look at a separate example. We're going to do that from scratch, at least one iteration, so you understand what we are doing. And then we're going to look at the minimization, how the problem changes when we're doing a minimization instead of maximization. And we're going to talk about identifying different types of solutions for your problem. And that will be the end of the lecture for today. On Wednesday, we're going to start using the computers to solve these problems. So let's go through these steps one more time. Okay, so step one, once you have a problem, let's say a problem that has more than 3 decision variables, or 3 or more, so you can no longer apply the graphical method. So we are working with the simplex algorithm for solving linear programs. So these are decision variables that can have positive numbers, positive values, and can be continuous. So they can assume fractional numbers. So if you're solving a problem in which the decision variables must be integer, we're going to look at a different algorithm later on this semester. This algorithm only applies for those problems in which you have linear equations, and also you're dealing with decision variables that are continuous, meaning that they're positive and they can assume fractional values. So the first step we do is to convert the problem, the linear programming model, into standard form. So what that means is you have your formulation, you're going to look at the constraints. If you have less than or equal constraints, you're going to add the slack variable. If you have a greater or equal constraint, you're going to subtract an excess variable. And if you have an equality, you don't have to do anything. So basically, you're putting all the constraints into an equation form. We discussed that already. Actually, the last problem of your exam was set up a problem into standard form. So once you set up your problem into the standard form, then we're going to obtain a basic feasible solution. For problems in which you have all constraints that are less than or equal to, which are the problems that we're studying right now, you're going to be using the slack variables to find that initial solution. Okay, so that will be easy at this point, since we are dealing with problems in which you have slack variables for each constraint. So it's easy for us to find an initial solution for the problem. And then determine whether the current basic feasible solution is optimal. We saw that when we have an optimization problem that is a maximization problem, we can look at the coefficients in the first row, or row 0, or the Tableau. And if you have any coefficient that is negative, that means that you have an opportunity to improve your solution. So we're going to look at always, once we complete an iteration, we look at row 0. Do you have a negative coefficient? We're dealing with a maximization problem. So if you have a negative coefficient, you say, okay, I have an opportunity to improve. So I need to do another iteration. And you're going to continue that process until all the coefficients in that row 0 are going to be positive. So that's how you determine whether or not the current basic feasible solution is optimal. Most likely, for your first step, you will not have the optimal solution right away. It's just going to be an initial solution. It's just your initial solution, and there's going to be room for an improvement. So you're most likely going to find a negative coefficient in row 0. If the current basic feasible solution is not optimal, determine the non-basic variable should become a basic variable, and which basic variable should become a non-basic variable to find a basic feasible solution with a better objective function value. So we decided from the non-basic which one is going to become a basic variable. We're looking at the highest negative coefficient in row 0. So that's how we know, okay, this one has a negative coefficient that is higher. So that will become a basic variable. In order to determine the basic variable that is going to become a non-basic, we are going to do the minimum ratio test, in which you are going to divide the right-hand side of the constraint by the coefficient of that entering variable. And then you're going to decide based on the minimum ratio test which one is going to lead. And after making those decisions, now you have to work with the coefficients of that variable that is entering your basics. So you have to make those coefficients zeros and ones. So that was we're going to use the elementary row operations to complete that process. And after that, we restart the algorithm, or not restart, but we go back to the step 3 to determine whether or not the solution we have is optimal. If the answer is yes, we are done. If the answer is no, then we have to go back to step 4, step 5, and continue the process until we find no negative coefficient in row 0. So those are the steps. Okay. So very important, make sure that you convert your problem into standard form. Once you have that, you can find the initial solution, and then you decide whether or not you have an optimal solution based on the coefficients of row 0. Negative coefficient means that you have an opportunity to improve, meaning that you can enter a new non-basic to the basics, and you can remove a basic from and make it a non-basic. Complete the elementary row operations, and then check back on row 0 if you have an opportunity to improve. Repeat the process. If you don't have an opportunity to improve, then you're done. You have found the optimal solution. So, any questions about this? Good. So, in performing the simplex algorithm, remember that we take the original objective function and we move the coefficients to the left-hand side. So those coefficients are going to become negative. And those are the coefficients that we want in row 0. This is the row 0 version. And we look at this example. So we went through the process of solving this problem. We have 3 constraints. We're 3 constraints, actually 4 constraints, and 3 decision variables. So again, all the constraints, I want you to pay attention to this. All those constraints are less than or equal to. Okay, so the problems that we're dealing with right now have less than or equal to constraints, all of them. So that's why we can find an initial solution easily. Later on, we're going to deal with different set of constraints with greater or equalities actually from the beginning. And you'll see that we're going to have to do an extra step to find that initial solution. But for now, we are dealing with this type of problems because they're easy to solve, or easier to solve than the other ones. So we're going to put this problem into the standard form. So that's why we add in those slack variables for each one of the constraints. And as I said already, we look at the initial solution for the problem. And that can be easily found by making the non-basics x1, x2, and x3. So those are going to be 0. And then we can solve for s1, s2, s3, and s4. And that will give us an initial solution. Simple for the case in which we have less than or equal constraints. So every time if we have a problem with all the constraints that are less than or equal to, we can find an initial solution by just solving for the slack variables. So that initial solution is here, and then the objective function is 0. So the next step is to make sure that we find out if we have a better, if we have an optimal solution. So again, we're going to look at the coefficients of row 0. And if we have an opportunity to increase any of those non-basic variables, and that makes the problem or the solution greater than 0, then that means that we can improve our solution. But remember that in the Tableau format, we move this to the left. So we're going to look for the most negative coefficient. So in this case, that will be 6. And then in order to decide who's going to leave, we're going to perform the minimum ratio test. So in this case, the most negative coefficient will be associated with x1. So x1 is going to enter. The minimum ratio test, we're going to look at the coefficients for x1, and we're going to divide that by the right-hand side of the constraint. So the minimum right there is 4. So that means that x3 is going to become a non-basic variable. So when entering a variable into the basis, we're going to do the right-hand side of row divided by the coefficient of the entering variable. That's the minimum ratio test. And the winner of the ratio test is the one that is non-negative. The smallest ratio is the largest value of the entering variable that keep the current basic variables non-negative. So make the entering variable x1 and a basic variable in row 3, since the row constraint was the winner of the ratio test 4 divided by 2, which is equal to 4. So this process is, so now after we identify who's entering, who's leaving, we have to do the elementary row operations. So this procedure is called pivoting on row 3. And row 3 is called the pivot row. So the final result is that x1 replaces s3 as the basic variable for row 3. And the term in the pivot row that involves the entering basic variable is called the pivot term. Okay, so this is how we set up the initial Tableau for a problem. You remember? I know there's a lot of color here, but if you go through the video from our previous lecture, you'll see how this develops. But the idea here is that you have all the coefficients from the initial formulation, and then we are performing that initial search for who's going to enter. So we see that for x1 minus 60 is the largest negative coefficient. So we know x1 is going to enter in row 0, negative coefficient. And then we perform the minimum ratio test. 40. So the right-hand side is 48 divided by the coefficient of x1, which is 8. 20 divided by 4, 8 divided by 2, and 5 divided by 0, which is undefined. So we don't take that one into account. So the minimum is 4. So at this point, what we have done is just identify if we can improve this solution. The answer is yes. Who's going to enter x1? Who's going to leave the basics s3? And then the next step is to enter x1 into the solution. So x1 is now taking the place of s3. So if you look at that first column of the top, at the top of the slide, that first column in red, you'll see that x1 is now taking the place of s3. So in order for that to happen, we have to make sure that that column for x1 is in the format of 0, 0, 0, 1, 0. And for that, we're going to perform the elementary row operations. So we did that work in class. What I want to do now is to work on a separate example, new example. So you have a chance to look at the process, at least for one iteration. So let's do that. I think that will make more sense. So I'm going to add a slide here. Okay, so this is the problem we're going to solve. The maximization of z equals 2x1 plus 4x2 plus 3x3 subject to 3x1 plus 4x2 plus 2x3 is then or equal to 60, 2x1 plus x2, 2x3 is then or equal to 40, and x1 plus 3x2 plus 2x3 less than or equal to 80. X1, 2. So all of those greater or equal to 0. Okay, so we have a problem in which we are trying to maximize this objective function 2x1 plus 4x2 plus 3x3. Those are three decision variables. And we have three constraints, 3x1 plus 4x2 plus 2x3 less than or equal to 60, 2x1 plus x2 plus 2x3 less than or equal to 40, and x1 plus 3x2 plus 2x3 less than or equal to 80. All those decision variables are non-negative, so greater or equal to 0. And we want to solve this problem using the simplex algorithm. So the first step is to set up these constraints into standard form. Okay, so we are gonna set up this constraint into the standard form. So this is 3x1 plus 4x2 plus 2x3 plus s1 equal to 60. Then we had 2x1 plus x2 plus 2x3 plus s2 equal to 40, and x1 plus 3x2 plus 2x3 plus s3 equal to 80. So now we have the constraint into the standard form. And we have 5 decision variables now, x1, actually 6, 2, 3, s1, s2, of them greater or equal to 0. So let's set up our initial Tableau. Basic variables. This is the row number, Z, X1, X2. Okay, so let's set up our first Tableau. So we have row 0, 1, 2, and 3. We have 3 constraints, and row 0 is always occupied by the objective function. So Z, remember that we set up our objective function in this way, minus 2x1, minus 4x2, minus 3x3. So we're going to use those coefficients for row 0. This is minus 2, minus 4, minus 3, S1, S2, and S3. All of them are 0. Okay, so we set up our objective function into the Tableau format. We move all the coefficients to the left. Z has a coefficient of 1, x1 has a coefficient of minus 2, x2 minus 4, and x3 minus 3. So those are the coefficients that I'm introducing into the table for row 0. So for the first constraint, another corner. So I'm using these coefficients. So for Z, this is going to be 0. For x1, that's 3, 4, 2. For S1 is 0. I'm sorry, and this is 60. So that's row 1, which for constraint 1. And we do the same thing for constraint 2. These are the coefficients. So for Z, 0, for x1 is 2, 1, 2, 0, 1, 0, 4. And then the same process for the third constraint. Coefficients 0, 1, 3, 2, 0, 0, 1, and 8. So I still have that first column, an empty column for the first column. I want you to help me fill out that one. So this is asking the basic variables for this problem. So we need to have 4. So what are those basic variables? The first one, or the easiest way for you to find out what the basic variables are, you have to find that identity matrix in your table. Right, so let me highlight the identity matrix. So you have first column here, second column here, third column here, and the fourth column there. Okay, so as I set up this, I need to know which are my basic variables. So if you look at the first one is Z, right? Because that's the first one here. The second one is S1. Third one is S2. The fourth one is S3. That's the initial Tableau. Any questions? Yes, yes, and that's going to help you identify what the basic variables are in this problem. Remember, the non-basics are the decision variables that have a value of 0. So what we are doing in order to find that initial solution, which is what we are trying to do here, is we are letting the basic variables to be x1, x2, and x3, because those are the ones that have coefficients. So if we make them equal to 0, we can solve easily for s1, s2, and s3. But if you look at this mechanically, that would be the easiest way for you to find an initial solution. You set up your identity matrix using the slacks, which in this case is what we have. We have 3 slacks. So we can set up those slacks, and those are going to give us that initial identity matrix really fast, because the coefficients are 0s and 1s for those slacks. So every time you have a problem with only with less than or equal constraints, like this one, that initial Tableau will look like this. You're going to find that identity matrix really fast. That would not be the case when you have constraints that are greater or equal to or equality. And we're going to talk about those cases in this class later on. Okay. But for now, I'm focusing on this because this is the easiest way for us to understand the algorithm. Then we're going to add those additional steps as we move forward. Any other questions? Okay, good. So we have the initial Tableau. So the question now is this an optimal solution? And as we learn, we're going to look at row 0, and we're going to see if there's any negative coefficients in row 0. The answer is yes. In this case, we have 3 negative coefficients, -2, -4, -3. So in order for us to decide which one is the one that's going to give us the best improvement, we're going to look at the negative coefficient with the highest value. Okay, so in this case, that's -4. So -4 is telling me if you were to include x1 as x2, I'm sorry, x2 as part of your basics, and you increase this value for something that is greater than 0, your solution is going to improve. It's going to be higher than 0, because right now, this is the objective function value right here. What we are saying is if you make x1, x2, x3 equal to 0, your objective function is going to be 0. And that's your solution. So you're basically saying, let's do nothing. We do nothing, we earn nothing. But that's not what we want. We want to have a decision for x1, x2, and x3, or a combination of x1, x2, and x3 that is going to increase our objective function. So basically what we are saying is, if you look at the coefficients of the objective function, the one that's going to give us the highest improvement is that coefficient of 4. You make x2 greater than 0, you make them x1, x2, and x3 greater than 0. The one that is going to increase your profit in this case, let's assume that this is profit, faster is x2. So x2 is going to give you the highest improvement per value of increments. So in that case, when we look at the Tableau, that's the meaning behind that. Finding that negative coefficient in row 0 is telling you that largest negative coefficient is going to give you the highest improvement if you decide to increase x1, x2, and x3 by 1 in this case. So the decision that we are making now is who's going to enter. The answer is highest negative coefficient right here, -4. So we made that decision. Now we need to identify who's going to leave. So we know that x2 is entering the solution. So who's going to leave is going to be based on the minimum ratio test, in which we are going to divide the coefficient of the right-hand side by the coefficient of that column for the decision variable that is entering the solution. So this is 60 by 4, 40 by 1, and 80 by 3. So this is 15 This is 40, and this is like 26.6. So the minimum between 15, 40, and 26.6 is 15. So that's how we decide who's going to leave. So in this case, S1 is leaving the basic variable set. And X2 is entering basic variable set. We identify who's entering by looking at row 0, largest negative coefficient. X2 is entering. We do the minimum ratio test to identify who's going to leave. The minimum is 15, which is associated with S1. So after making those decisions, we made S1 leaving the basic variable set. X2 is now entering the basic variable set. Any questions? So if you understand up to here, then you understand the algorithm. Because what we're going to do now is repeat this process. Obviously, we have to make the elementary row operations now. Yes. Yes. So that's a good question. So what does that mean? So at the beginning, when we are trying to find the initial solution, if you remember, we have a set of basic variable sets and a set of basic variables and a set of non-basic variables. So we are making those decision variables that we are making equal to 0 to find that initial solution are the non-basics. So we are making X1, X2, and X3 non-basic variables. And the set of basic variables are Z, S1, S2, and S3. And this goes back to our discussion of how the simplex method works. So if you remember, we have n decision variables, m constraints. So in this case, it's m minus m is 3. So we can make 3 decision variables equal to 0 and make them the non-basics. And then we can solve for the rest. So that was the intention of that last assignment, in which you were making this set of variables, non-basic variables equal to 0, and then solving for the rest. Is the same idea. What we are trying to do here is we find an initial solution, and now we're changing this set in order to find the combination that is going to give us the optimal solution. But now we are doing that search more in a smart way. We are not just looking at all the possible combinations like we did in the assignment, and we were listing all of them. Now what we are doing is we can identify which one is going to enter and give me the best improvement by looking at these row 0 and ratios. By performing those decisions, we are making sure that we are moving in the direction of improvement. So we don't have to search for all possible combinations. So to answer your question, remember this n minus m. So that is going to give you the number of non-basic variables, which you can make equal to 0. In this case, we have 6 and 3 constraints. So that's 3. So we can have 3 non-basic variables. We can make those equal to 0 and solve for the rest. So we made these 3 equal to 0 and we solve for the rest. And that's the solution that we got for the first Tableau. Now the question is this an optimal solution? The answer is no, because we know that we can improve. So if you want to make any of these 3 different than 0, you have to remove them from here, make them basic. and then take one of these and make it non-basic, which is what we are trying to do with these ratios. We identify that x2 is now becoming a basic variable. So x2 is going to move to this set. And what this is telling me is S1 is going to move this set. So if I move x2 to the basics, I can make x2 greater than 0. If it is not part of the basics, it has to be 0. So any variable that is part of the non-basics will be 0 always. So now that we haven't made the rotation yet, if you look at this Tableau, x2 is still non-basic. We're gonna make it a basic variable now with the next iteration. So that's why we need the elementary row operations. Let me see if I can fit that here. So I'm going to create another table. Okay. So as I mentioned, we are going to make x2 part of the basics and s1 is going to leave. So I need to fill out this first column so I don't get confused. So use another color here. So z will stay the same. S1 is going to leave. X2 is going to take that place now. So X2 is going to take the place of S1. And I'm identifying that here. The S1, S2, and S3. Now I know that X2 is going to enter, S1 is leaving. So X2 is entering here. And then I have S2 and S3. This is 0, 1, 2, and 3. Okay, so if I know that X2 is going to take the place of S1, if you look at the column for S1, the format of S1 is 0, 1, 0, 0. So I need to make that column for X1 now 0, 1, 0, 0, referring to this column right here. So S1 is leaving. The format of X1, the column for X1 needs to look like the column of S1. So I'm going to use elementary row operations to make that happen now. Okay, so what this means is this 4 coefficient here needs to be a 1. So how are you going to make that equal to 1? You're going to multiply row 1 by 1/4. So what this is saying, so now I'm going to multiply this by 1/4, and I'm going to put that result here. So that will be 0. This will be 3/4. This is going to be 1, 1/2, 1/4, 0, 0, and 15. Okay, so I got the 1. Now I need to make the rest of that column 0.
After your row 0, doing closing it by 1/4. But once you get like the negative.
So we did, this is row 1, and we did 1. We haven't done 0 yet.
Okay.
We're gonna do.
I'm just saying, would it matter if we got a negative?
No.
No?
Well, that's not gonna. You're meaning this value or here?
Yeah. So what about
This.
Yeah.
It's not gonna be a -2 because we need to make sure that this is 0. So we're gonna multiply by 4 this column, and we're gonna add that to row 0. Okay. So those are the elementary row operations. So we made this 1. Now I want to make this 0. So I'm going to multiply this row by by 4. And then I'm going to add it to this one.
Yeah.
So if you multiply by 4 row 1, and you multiply by 4 and you add it to row 0, this is going to be 1, 0, minus 1, 1, 0, 0, 60. So remember that this value is telling you your objective function value. So what we are saying right now is x2 is going to be 15. If you plug it into your objective function, that value, 15 times 4, this value should be the same. So 15 times 4 is 60. So that means that we're doing this right, correctly, right? So objective function 60 because x2 now is 15. So we have improved our objective function. So let's continue. So now I need to make this guy 0. So I'm going to multiply this. Oops, that's nice. So I need to make this guy, this guy is 0. This guy. So I'm going to multiply this. See how can I make that? Maybe use a different color. So now I'm going to multiply this by -1. And I'm going to add it to this row. So that will be 0, 5/4, 0, 3/2, minus 1/4, 1, 0, 25. Let me double check those numbers. So 3/4 minus 3/4, 8, yes, 0, minus 1/2, plus 2 is 3/2, minus 1/4, plus 0 is minus 1/4, minus 15 plus 40 is 25. Yes. So you see the column for x2 is now 0, 1, 0. We need to make the last one also 0. So what would be that step? How are you gonna make that 0? And we're talking about this value right here. You have to multiply by -3 and then add it to row 3, right? So I made this right. This will be 0 minus 504, 0, 1/2 minus 3/4, 0, 1, 5. So that enters x2 into the basics. Have completed an iteration. So now we'll go back to step 3, check if we have an optimal solution. You look at row 0, do you have any negative coefficient? The answer is yes. We have a -1, so we are not done. That means is this guy can enter the solution, and we need to find out who's going to leave. So we do the minimum range test. So this is 15 over 1/2, and this is 30. Then we have 25 divided by 3/2. This one? Let's check. So -3. This is -45 plus 80, right? That'll be 35. Yes. Thank you. Correct. That will affect this, right? So now we have 50 divided by 3. That's a fractional number. So how much is that? Do you know? 50 divided by 3. That is like 1, 2, 16 something, right? And then we have 35 divided by 1/2. So this is 70. So that means that this guy is the minimum. So S2 is leaving. So I'm gonna stop this exercise because you can work this on your own. We have to complete the lecture, running out of time. So, so the process is the same now. You know who's going to leave? S2. X3 is gonna enter. You're gonna put X3 now here, and then you're gonna make X3. That column looks like this S2 column. Any questions? So I think it's gonna be a good exercise for you to complete on your own. And then if you have questions, we can talk on Wednesday. But hopefully this clarifies some doubts. And again, good thing about technology now is that you can go watch the video. So after class, I'm going to upload the video again. If you go back, check step by step what we did, that should help. Once those coefficients in row 0 are positive, then they are done, meaning that you have an optimal solution. So your solution is going to be given by the values of these basic variables, and those are going to be stated in the right-hand side. So at this point, we have x2 equals 15, s2 equals 25, s3 equals 35, and an objective function of 60. After completing the next iteration, hopefully all this is going to be positive. So your solution is going to be stated in terms of x2, x3, and s3. Okay?
So we have the S2 is leaving now,
S2 is leaving,
and X3
is entering. Yes.
and then you make X3 equal to 0.
Then we are going to make this column 0, 0,
Yeah,
1, 0.
and this will be the optimal solution.
At this point, you're going to check row 0. If there's no negative coefficient, that's the optimal solution.
Yeah, so there will be no.
Yes. Okay. Any other questions? Okay. So remember that this discussion applies to maximization. So I'm sorry, this is from the previous problem. So this is the summary. Okay, so now this is where we stopped last time. We want to apply the algorithm for minimization problems. So the simplex method can be used to solve minimization problems in two different ways. Consider this linear programming model. Method 1, the optimal solution is the point x1, x2 that makes z equals 2x1 minus 3x2 the smallest. Equivalently, this point makes maximization of minus z equals minus 2x1 plus 3x2 the largest. So this means that we can find the optimal solution to the LP by solving this problem, in which what we are doing is we are changing the minimization objective function to a maximization, but we are multiplying the objective function by minus 1. So what you are looking at is the maximization of the negative objective function. That should give you the same solution as minimizing the positive coefficients. I would not prefer that. Okay, I prefer method 2. I think this is a little confusing. So let's look at the summary. Multiply the objective function or the minimization problem by minus 1 and solve the problem as a maximization problem with the objective function minus z. The optimal solution to the maximization problem will give you the optimal solution for the minimization problem. As a note, you have to remember to multiply the value of the objective function at the end by minus 1. So for example, solve the LP shown to the right using the simplex Tableau method. So we have the minimization problem, 2x1 minus 3x2, these two constraints. So using method 1, we are multiplying the coefficients by minus 1. So this is minus z equals minus 2x1. So this objective function using method 1, you are saying that this is going to be a maximization of minus z equals minus 2x1 plus 3x2. And then when you move these coefficients to the left-hand side, you have minus z plus 2x1 minus 3x2. So when you set up your table, that's what you have. You have a positive coefficient for x1 and a negative coefficient for x3. That is because you have set up this objective function in this way. Minus z plus 2x1 minus 3x2. So your coefficients for x1 and x2 are right here. Minus 2 positive, minus 3 negative. And then you solve the problem as we have discussed by looking at the minimum ratio test. Since you are maximizing after the first iteration, all the coefficients are positive. So that means that you have found the optimal solution. The optimal solution is minus z equals 12, x2 equals 4, s2 equals 10. So now you have a negative coefficient in your objective function. So actually you have a positive coefficient here. So in order to get that solution, you have to multiply by -1. So that's why you end up with -12. I don't prefer this. I prefer the other method. I think it's more confusing. You have to do you have to remember a lot of details. What I would prefer to do is to, instead of, we're gonna proceed as we did for the maximization problem with a little change. Simple modification of the simplex algorithm can be used to solve the minimization problem directly. So we are gonna modify step 3 of the simplex algorithm as follows. All known basic variables in row 0 have a non-positive coefficient. The current basic feasible solution is optimal. If any non-basic variable has a positive coefficient, choose the variable with the most positive coefficient in row 0 as the entering variable. So instead of when we were maximizing, we were looking at row 0 and we're looking for the largest negative coefficient to decide whether or not, we were looking for a negative coefficient to decide whether we have an optimal solution or not. That's for maximization. And if we found that all the coefficients were positive, then we decided that we found the optimal solution. What this method is saying is, let's do the opposite with minimization. Let's search for the positive coefficients in row 0. If we have a positive coefficient, then we enter the largest positive coefficient. If we have all negative coefficients, then we have found the optimal solution. That's it. That's the only difference. So when you're maximizing, you're looking for all coefficients to be positive in order to make the decision that this is an optimal solution. If you find a negative coefficient, then you know that you can continue. For minimization, now we're going to do the opposite. We're going to look for all negative coefficients. If we find all negative coefficients in row 0, that means that we have found the optimal solution. But if there's a positive coefficient, then that means that we have to continue. Okay, so that's the modification. This modification of the simplex algorithm works because increasing a non-basic variable with a positive coefficient in row 0 will decrease the value of the objective function. So let's look at the problem again. Now we have the objective function, -2, these are the coefficients for row 0, -2, 3. So remember, when we were doing maximization, we were looking for the largest negative coefficient to enter a decision variable. Now we are minimizing, so we are looking for the largest positive coefficient. So that means that x2 is entering. We perform the minimum ratio test. It is 4 divided by 1 is 4. 6 divided by -1 is not defined. Well, it's negative, so we don't use that. So we only use the positive coefficient. So that means that row 1, which belongs to S1, this is for, let me make this basic variables, Z, S1, and S2. Yes, go ahead. Say that again? Access variables. These are less than or equal to constraints, so we use slack variables. Yes. So that's why we have the slacks. So we were here. Yes. So x2 is entering, largest positive coefficient. This is a minimization problem. S1 is leaving, minimum ratio test. So after performing the elementary operation, you see this is now 0, 1, 0. We're going to look at the row 0 coefficients. There's no positive coefficient here, so that means that we have found the optimal solution. Optimal solution is minus 12 with x2 equals 4, s2 equals 10. Is the same solution that we found using method 1. I prefer this method. Just have to remember, when you're maximizing, this is what you look for. When you're minimizing, this is what you look for. If you keep that in your mind, or if you remember just one, you know that you do the opposite for the other one. Okay? So that's how you solve problems in which you are minimizing. Yes.
So you have access variables?
Not yet. And we're going to get to that point. Because right now, what we are assuming is that our problems, or the problems that we are solving, have constraints that are less than or equal to. After we work with the computers on Wednesday, next week we're going to look at problems in which we have greater or equal to, in which you're going to have the excess variables, and also problems with equalities. Those are managed differently because we're going to have to do an extra step to find that initial solution. Yes, yes. So your question is right. We're going to get to that next week. Okay. For now, I'm more interested in you understanding the basic steps, how the algorithm works, because what we're going to do after is going to be adding more stuff into what you are learning right now. Okay, so this discussion should help you complete the assignment that is due on Wednesday. And then after that, we're going to get into what we call the artificial solutions, in which we're going to be dealing with the excess and artificial variables to get that initial solution. So this is the minimization problem. So the last part of this lecture is to understand if you have alternative or multiple solutions, unique solutions, and based on the information from the Tableau. So for some LPs, more than one extreme point is optimal. So if an LP has more than one optimal solution, it has multiple optimal solutions. So if there's no non-basic variable with a 0 coefficient in row 0 of the optimal Tableau, the LP has a unique optimal solution. So if there's no non-basic variable with a 0 coefficient of the optimal Tableau, the LP has a unique optimal solution. If there's a non-basic variable with a 0 coefficient in row 0 of the optimal Tableau, it is possible that the LP might have alternative optimal solutions. So we're going to look at the non-basic variables. We see a 0 coefficient for a non-basic. That means that the problem might have multiple solutions. So let's look at this example. Solve the following LP using the Simplex Tableau method. So again, we have less than or equal constraints. So we're going to add the slack variables. We are maximizing. So these are going to be -2 in row 0. We're going to have a slack here and a slack here. So that's what we have, -2, -2. We have a slack variable here, another slack variable here. So setting up this, we have two negative coefficients that have the same value. So we choose arbitrarily. They have the same value. So we are selecting X1. So X1 is entering the solution. And then we do the minimum ratio test, and S1 is leaving. So X1. So after iteration 1, we have enter X1, and we found the optimal solution. There's no, if you look at row 0, there's no negative coefficient, so that means that we have the optimal solution. However, you remember from our previous slide, we look at the non-basic variables, which are S1 and X2. The non-basic variables are the ones that are not in this column. Okay, so this is Z, this is X, this is X1, and this is S2. Okay, so X1 and X2 are the basics. The non-basic variables are S1 and X2. So if you look at row 0 for X2, it's a 0. So when that happens, non-basic with a 0 in row 0, that means that we can have alternative multiple optimal solutions. So the solution is xz equals 12, x1 equals 6, x2 equals 2. But if we solve, you remember this decision that we make here? Instead of choosing x1, we choose x2 to enter. We can solve the problem. You'll find exactly the same solution. X2 equals 6, which is going to give you 12. Is another solution with an optimal solution equals to 12. So in this case, this will be x2 S2. And so if you remember when we're doing the graphical method, you have something like this. Let's say a feasible region like this, and we were doing the isocost. Let's say something, this was our isocost. So when we move the isocost in this direction, it was going to overlap this. And if your optimal solution was here, you knew that if that isocost was overlapping the whole line, all those points in that line were optimal. This is the way that we identify that using the Tableau. We say, okay, we found an optimal solution, but you see there's a non-basic with 0 coefficient. That tells us that we can find an optimal solution using that as well. See, alternative optimal solution, same solution. Unbound, for some LP, there exist points in the feasible region for which Z assumes arbitrarily large or arbitrarily small values. When this occurs, we say the LP is unbound. An unbound LP occurs in maximization problem if there is a non-basic variable with a negative coefficient in row 0 and no constraint that limits how large we can make this non-basic variable. Specifically, an unbound LP for a maximization problem occurs when a variable with a negative coefficient in row 0 has a non-positive coefficient in its constraint because the test ratio test failed. So for example, we look at this problem, what we are trying to say is, we know X2 is entering after iteration 1. The second Tableau, we make X2 part of the basics. X1 is going to enter. Iteration 2, we have this result. And now you see there's still a negative coefficient here. S2 has a negative coefficient, so we have to enter S2. But when you do the minimum ratio test, since both of them are negative, you cannot perform the minimum ratio test. So you're basically stuck at this point. What this means is this is an unbound problem. You are not going to find a unique solution for this problem. What this means is there's, for the direction of improvement, if you remember, we have a problem like this, and we have X1, X2, and we were defining our feasible region like something like this, and this was the feasible region. So there's no bounds here at this part. So if your direction of improvement is that direction and you're maximizing, there's no way for you to find a unique point. You're going to still increase because the area is increasing. So that's what this is representing. When you get to this point, you're entering, you decide that X2 is going to enter, but when you perform the minimum ratio test, you have 2 negative numbers. You cannot perform the test. So what this is telling you is this is an unbound problem. We would like S2 to enter the basics, but there's no row in S in which S2 has a positive coefficient. Therefore, the LP is unbound. Okay, so that concludes this discussion for the simplex method. If you have an assignment, please work on that. On Wednesday, the plan is to transition into the computers so we can solve these problems using the computer. And you're gonna learn how to use Excel to solve linear programming models using the simplex method. And then on next week, we're gonna deal with the problems that have constraints that are greater or equal to or equalities. Any questions? Mhm.
There is a new software for example, like besides Excel.
Yes, yes,
Professional.
yes. So there's Ample, and we're gonna look into Ample as well. And there are several computer packages that are for sale that can be used to solve these problems.
And computer world company.
Mhm. So that's yes. So the question is really good. In a practical setting, meaning you're in the industry, would you use this type of I'm sorry, the computer packages you're talking about? I mean, you will use optimization because this is for decision making, as we explained in the applications, the formulations for scheduling, for production planning, for all those type of problems, you're going to be using optimization. Computer packages, it depends on which company you end up working with. Typically, based on my experience, everybody has Excel, so that's why I start with Excel. There's some open source add-ins that we can put into Excel to solve larger problems. And then from there, we have Ample, which uses Simplex, and we're gonna use Ample also in class to solve these problems. And then we have some advanced, I think, elective courses that Dr. Novoa offers in optimization, that she also goes into Express, which are other software packages. I think she also teaches MATLAB to solve these problems. So in this class, we're gonna use Excel and Ample, and then in those advanced optimization classes, she uses MATLAB and I think Express. So yes, we try to show you all of them because when you go to industry, you don't know which one you're gonna be using or which one they prefer. But most likely, I think all of them will have Excel, so you will be able to solve at least using Excel because I know everybody owns Office in their computers. Good. Any other questions? Yes, yes. So I can start passing that information. It's free for the students. Actually, we since we have a student license, you can download it to your computer. So I will find out how to pass that information to you guys, so you can install it in your machines. Any other questions? Good. So I'll talk to you. See you on Wednesday. Yeah, so I have graded the exams already.